So let's start with the week 7. Today we will talk about statistics and probability. Well, the topics that we will talk about in the lecture. So, like, honestly, probability, there is a whole class talking about probability theories and everything. So I will try to kind of compress maybe just some of the basic understandings into today's class. And then I guess applied probabilistics is something we call statistics. So I will try to talk about some of the more practical uses of probability. And then we will slightly also touch on visualizations. Yeah, so I think today's programming section will be relatively short. I'm planning for maybe the next week also to include some more kind of like the practical statistical analysis that I used on some data before, and so maybe show some of this here as well. So kind of like really show from practice of how some of these things can be used. But I think just to separate it all out, I will kind of split it into today and the next classes. Okay. So let's start with probability. What is the purpose of studying probability and statistics? So this is sort of like a view of me as a machine learning researcher. So maybe like not everyone will tell you some similar definition, but this is sort of exploring events in the real world and trying to model them. So you have some sort of like measuring device, and the device is measuring, I don't know, the amount of tremor somewhere happening, or the types of lights which are coming off some like thing that you are looking at, that you are trying to explore. And that is an event happening in the real world, and then you are trying to kind of find whatever its behavior is, and then make a model which would kind of correspond and explain it. Okay, and so to maybe show that on some plot like this, let's imagine that this is some behavior that we see in the real world. So maybe these values, this from -4 to 4, is some like maybe different types of events we see, and then this number from 0 to 5 is how often we saw that occurring across our measurements. So it's a histogram actually. So if you see a bunch of zeros happening, which we saw actually, then we have a really high amount here. And then what we can see that like the amount of maybe values which we recorded as around 2 was somewhere around here, fine, but it was really rare to see numbers which were really really large or really low. And so this would be some sort of like raw measurements that we have from the world around us, and then we try to maybe somehow try to explain what is happening, and then maybe have a model. And so this whole section is called modeling and sampling, because we want to create some model. Okay, and so again, how to describe this? These are number of occurrences of like that event with this strength, right? So with like, yeah, with this number happening in some measurements with these occurrences. Okay, and so the idea of modeling is basically to figure out a way how to create this like nice plot. This is a model, or this is our theory, or like a hypothesis how this is working. And we kind of hope that if we put this line somewhere like here, then it would correspond to the underlying data. So we kind of want to create models which correspond to the data that we see. And so why I was prefacing all of this with the fact that this is a machine learning researcher's point of view is because quite a lot of machine learning is actually like having some input data, and then instead of having this nice one line, we actually place the model there, and then we want it to sort of like behave the same way. But in machine learning, it's not mathematically explained. In that case, this curve is not like this nice curve, but there is a black box which is doing something. So I guess that would be the distinction between studying probability and then studying something applied with machine learning is that in that case you have some models that you train, but they are sort of black boxes. Whereas in this case, with probability and statistics, we have some models as well, but these are described quite like these are described mathematically, and they have some nice behavior around them. So if you find a probabilistic model which fits the data, then you can say all sorts of things from that. So yeah, it's also like an older field, so there is more about that. Okay, so well, just to briefly just to summarize all of that, we somehow want to create a model, so which is this line, and we want this model to somehow correspond to the data. Okay, so we end up with a model which is this line, and there then comes the next part. If we have this model, we would like to kind of figure out what can happen, right? So this is, for example, something that can be used in a simulation scenario. So we have this line, and then maybe this line has been modeled on the data that we saw from from some measurements in the nature. And so if we want to maybe make a game where the same effect is being replicated, there is the same effect happening, we will use some model like this, and then maybe we can just sample some random points which would correspond to this. And so like you can maybe notice, I'm slowly changing the terminology and kind of bringing in new terms. Modeling is one of those, and then sampling is the other one. Okay, so we can call these the raw measurements. When creating like an abstract model, we can call this modeling, this point, this way, sort of. And yeah, going from measurements to an abstracted model. Yeah, like there can be good models which correspond to the data, or there can be bad models which don't correspond to the data at all, but we will kind of talk about that later as well. And the other part, kind of the other way around, if we have a model and then we want to go from it back into samples, that's called sampling. So basically that is, yeah, I guess it's like predicting how it's going to be, or maybe in simulation scenario, we kind of want to generate some samples which sort of look like, behave like this. Okay. Okay. So as you all know, real world is really noisy, which means that when we have measurements, very rarely we would have measurements like this, which really look like, yeah, this is the hill, basically. This is what we have. Quite often we would have quite a lot of like holes in it, and maybe the measured data would not really represent whatever we want to fit there, because there is a lot of noise. And maybe the noise is actually in our measuring devices. So we have this, maybe this is like this is an illustration. Here is a true signal, so there is someone making this signal in some circuit. And in our measurements, we actually see just all sorts of values around that. So we still kind of can maybe distinguish the shape from it, but who knows how precise our measurements actually are. And so when you are sort of going from the measurements into the model side and then actually back as well, so from model side back to the like samples, we have to keep all of that in mind, that there can be outliers in our data, some noise. Okay. Yeah, I mean, this is also because real world often isn't just some like bunch of data here which could be easily modeled. There is a lot of diversity, and so like a lot of samples which are falling away from some artificial model, right? And so this is actually good, right? But we do have to include all of that to our models. So when creating this theory, this model, we somehow need to in that process we somehow need to make the modeling process robust to noise. So usually this means that in some maybe visualization or something, you cannot show like all the data, and maybe there are some outliers which you can still show, but then like ignore in the way that you just show whatever works best for the model. Okay, this goes both ways. So ideally, if we have a model which was something like this, we do still want to every now and then to have samples which are really rare as well, because that's how real world works, right? So we do want the model to be able to produce their own sort of like all sorts of data. It's not enough to just produce zeros all the time, because we know that it's all between -1 to 1. We would lose all of these samples. Okay. So I guess there are some model types which maybe focus too much on the average sample, and then those models are not working as well as they could. And so I will show you an illustration which is kind of from a different field. It's from machine learning, and it's also like comparing two models, but they do show this exactly this concept of like either focusing too much on the average sample or actually allowing the details. And so it's a nice visual illustration of showing what it means to kind of just reduce the data on the average, whereas to include all the details in there. Okay, and so without going into the details of what this is, it's kind of too much. These are images that are kind of generated faces, so none of these persons are real. I guess they are relatively real. They are coming from some dataset of faces of celebrities, I guess, and so the model there was used to kind of create faces. And so there are two possible models. One of them sort of results in these blurry faces, and the way that model works is the variational autoencoder, this one. It doesn't really you don't have to know exactly what the model is or how it's working, but just to kind of show it. This one always strives for images which are sort of the average one, because in the process of learning the information into this, it's forced to lose a lot of information and kind of just keep the important ones, the important sort of features. So it will throw away all the sort of higher frequencies of the information and just keep the lower frequency of that, right? So something like this may happen also in compression with sounds, I think. And so there is a better model which kind of follows in research. This was coming first, and then they figured out another model which was called GAN, and this one allows to sort of include all sorts of details in there as well. So I don't know if this is really images produced by the GAN, but they would look like this rather than like this, right? Because the first one is kind of just keeping the average features, while the other one is sort of also learning the details. Okay, so like showing this here, basically one of them would be focusing on the numbers which are the most probable ones and sort of ignoring everything else, while the other one would actually also include all of these samples. Okay. Okay, so I will talk a little bit about some terminology. So probability has a lot of terms and a lot of like new concepts which don't really bring that much new. They are actually really simple, but a student can get really lost and really fast inside the whole terminology that they are using. I'm quoting case of mine where I was studying the course of probability, and sort of before discovering that this one thing that we are studying about for 3 hours or something, or 3 weeks, is actually really simple, and it's just some applied rule. You got to chew through tons and tons of terminology and then extract the knowledge. But I guess then it kind of allows people to build up on the terminology. So they will, when you get into the probabilistic theory a bit more, you can start using those terms and kind of explore for what's possible with some rules there. But we will not get there. We will sort of stay in the more practical side of those things. To to describe a little bit what you were seeing in all of these previous plots on the previous pages. What you saw here, so this model, this line, this is a model which is called the normal or the Gaussian random model or the distribution. And so this one works that it has some center, which is in this case the 0, and all the samples are within that, like around that center, around that mean value in some distance. And so there are some terms that we will go later into, which describe the mean, so the value that's this is settled around, and then the kind of how wide can it go. That would be the standard deviation of the model, right? So maybe to return slightly to the term here, which is important, that is the probability density function, and that is the way how we visualize the probability function that we are using. So it's the way how we have shown here the orange line. Okay, so what that means exactly, how to read it, we will look into that in the few next slides. We were also talking about like measuring some event or some behavior happening in the real world, and if this is an independent source of random behavior, we call it as a random variable. So soon after this, there is a lot of more terminology which becomes really hellish. And so for example, independent source, how do you how can you be sure that anything in the nature is actually independent from other things that you could be measuring? It's a whole like that's what you have to care about, and we will not right now. But yeah, so there is a lot of the stuff hidden there as well. So maybe these are sort of like idealized examples of how nicely it would work if everything was sort of behaving like this random, normal or Gaussian random function. Okay, cool. So we mentioned the probability density function, PDF. How can we read that? Well, so there is some maths definition here. Basically, that when you look at some interval, so from minus 0.1 to minus 1 to plus 0.1, sorry, this interval, then the probability of like you getting a number between these two is equal to the area of this area, which is something that later in maths can be calculated by integration. So like you start here and then you're slowly adding every bit here. You can also like calculate it in a simplified way of just this side times this side plus there is something you have lost, so maybe you have to mimic it somehow still. But yeah, it doesn't really matter how that much how we actually calculate it. But this would be the explanation, and it's not really that clear what this means. But this sort of already includes the notion of imprecision of measurements. So, for example, the probability of getting like measuring values which would be exactly 0, and let's imagine this is like temperature or something, not 0.0001, but exactly 0. It will not really happen. You will always have some noise which is moving it to the right or to the left. So that's why people in probability really like to talk about like these ranges. Okay. Okay. So this was sort of more mathematical explanation. How can we understand it intuitively? Is that this plot really tells us which numbers are the most probable, right? So something around 0. If we have this as like let's imagine that this is our model, and we will be getting numbers from it. So it's a function that we can call again and again, and then it will just give us numbers. And like it's a generator sort of. So if we generate numbers from that, most of them will be around 0. So the largest probability would be around 0 because that's the highest peak there. And sort of the further you get away from the 0, the smaller the probability of getting that number. And you can kind of see that maybe like 0 up until maybe minus 1.5 and plus 1.5, or maybe minus 1 to 1 is where most of the numbers will lie. But still you will be getting these lower numbers every now and then as well. So that would be how you are reading this one. Okay, so we talked about probability density functions. They don't have to be fixed with just this, the Gaussian. They don't have to be, with the Gaussian model, with the normal function, there are different types. For example, this one, where when we look at it, it's called uniform probability density function. When we look at it, like the probability of getting anything from here or from here is 0. But all the numbers that you will be getting will be from 0 to 1. And all the probabilities of getting those numbers will actually be the same. So this is a uniform random distribution of getting numbers between 0 and 1. Right. And so sometimes you actually want models which would correspond to this, because there are things in nature which kind of fit in with this model better. And sometimes you actually want to be sort of like very fair and be able to get numbers between this range all with the same probability. Right. Okay. So we talked about these models, right? We talked about these sort of normal models, and then these which would be uniform models. So normal probability density functions and uniform probability density functions. There are, if we had just these kind of, if we are always stuck around having the one which goes from -4 to 4 and then one which goes from 0 to 1, we would be, that would be boring. We would not have enough models to model the whole world, right? So that's why these models tend to have some parameters. And so these models have parameters which influence the way the shape of their probability density function is, which we will see on a slide in a visual way. And for example, we can have the same sort of function, so the same, let's say, Gaussian function, which was created with different parameters. So one would be sort of fitting the data better than another one. Okay, so what this means on an example of the uniform distribution is that the parameters for uniform distributions are A, B, which is basically, this looks like a function in Python, right? This is easy. So we create this as a distribution between the first number and the second number. So this would be u from 0 to 1, and this is u from 0 to 3. In this case, we are getting all numbers with within this range with the same probability. Whereas in this case, we are getting numbers within this range with the same probability. So you can notice that this one is higher, this is 1, and this is somewhere around 0.3, I guess. Well, it's because this area is larger, and so all of this has to sum into 1, because that is the probability of wait, I got lost in this. How to explain it the best? Well, so I guess when looking at these two samples here have the same probability of falling in between 0 and between 1. And samples here have the same probability of falling between also two numbers, but the area there is larger. So the actual probability of the number being here is smaller. But it doesn't really matter. When we look at the graph, it's still the same, because all these numbers have the same probability of kind of falling out from this generator. Okay, so this can also happen with Gaussian functions or the normal functions, and this one is defined by two parameters like the previous one, but in this case the two parameters might mean something else. The first one is called mean, and that's the number where this hill is kind of where its highest peak is, so where it's sort of around. So that is the number which will be the most probable. And then the second number is the deviation, the standard deviation, which is telling you how wide this hill will be. And so if we have a low number for the standard deviation, it will be really sharp, this hill, and kind of the numbers that you can generate from it will be very close to this range. So you will be getting way less of these sort of outlying numbers. Whereas the number, if this is decreased, the hill will sort of be more flat and more flat. So in this case, you can get actually numbers which are really high or really low with some decent probability. Okay, and you can sort of change these two parameters in order to move this model around. Okay, and so right. Okay, so one more model that we will introduce, and that is a mixture of normal distributions. So when we're looking at the normal distributions, which is just with this one hill, you can also have a model which is somehow including more of these previous models. And so the probability of sort of one event would be this one, then probability of another event would be this one, and then probability of another event would be this one. But then when you add all of those three probabilities together, you end up with this sort of curve. And so it's a way how to model a more complex behavior which is happening somewhere in the nature, where maybe there is not just one peak, but maybe there are two or up to three or more. I don't know however many we need peaks in the data that we are seeing. Okay, so each of these models, each of these so it's a mixture, meaning a combination of some previous normal distributions, and each of those previous normal distributions has its own parameters. So these seem like they would have the same standard deviation, but they would have a different mean, because this one is centered around 10, this one is centered around 5, and this one is centered around 15. But in combining them, you can sort of have a different curve, which is maybe corresponding to something in the nature better. Okay. And so to relate all of this back to the start of the class when we are talking about modeling, probability and statistics gives us these models as sort of possible instruments that we can use with different measurements that we see. So let's say we see all of these blue things happening in the nature, and then we are sort of tasked with finding the best model to represent this. And so we kind of, let's say we are choosing between the uniform one, because it would be between 0 and 1, or with the normal distribution one, which would be from somewhere around 0, but going here or here. Well, neither of these models is the best one, so we probably actually have to change these parameters and find the one which would correspond to this the best. Right. So the task of modeling becomes to pick the best model, so sort of figure out if I want to use a normal distribution or the uniform one, and also to find the best parameters for that model. So for example, I think something centered around here would correspond the best, and probably the normal distribution one would actually fit better as well. And so something like maybe having 1 here or 0.5 here, I guess, and then having maybe, I don't know, like 1 or still maybe 1.5 or something would be a better model. So the choice then becomes one, to choose the better model, which is normal distribution in this case, and then also to choose the best parameters. So that's called fitting the parameters or fitting the model to the data as well. Okay. Yeah, note that this is like a sample which has been generated just for this class, so it's simple and you sort of can see it. But in the real world, often things are more complicated, so they cannot be really fitted with just one model like this. Okay, so what does all of this mean for us when we want to sort of use these functions? Well, this sort of illustration of the concept is helpful in maybe showing where the samples will be falling from, or maybe comparing two models next to each other. But we can also just use them and then show what is the distribution of the samples that they would be showing on an image. So this is something that we will be actually sort of doing in today's class practice in generating these images with like coloring the pixels depending on a random distribution. So if we have a uniform random generator, or uniform like a random generator which is working with uniform probability distribution, then we would be getting something like this. So this is basically some white noise. The probability of all the samples being either white or black is the same everywhere, regardless of like the position in the plot. Whereas a normal probability distribution function, if we used that as a generator, we would be getting numbers around the mean of this, right? And so let's see, this is 0 and 0 because of this mean. And so the most samples that we will actually color black will be somewhere around this point. And so this is like a visual illustration of why why understanding why those how those models work and what models we can even use. Why is it useful? Is because then you can sort of like have an intuition behind why are we getting this sort of image or this sort of image. Okay, and so there is a up until now, is everything clear? Or is it more clear now after the... Okay, cool. So right, so there is a lot of more complexity in probability theory. Some of it is, for example, talking about correlation and causality. And so if two events are somehow related, they are correlated, means that one is somehow influencing the other, but it doesn't necessarily mean causality, and causality is that one is causing the other. And so often we have multiple events happening somewhere at the same time in the nature, and we somehow want to kind of figure out if there is a causality, if one is causing the other one, or only correlation, and how strong that correlation is. So they are related, but it doesn't mean that one would be causing the other one. And so to disentangle these two terms is quite difficult, and in measurements sometimes you basically cannot even say if it's you cannot eliminate the possibility that all of those dice that you threw were always, for example, falling to 1. That could be just a really small chance, but still could happen, and that's not the same thing as like saying a rule: if I roll a die, it will always be this thing. So there is something different between being able to say that some two effects are correlated, or that something is causing another thing. Well, maybe the die wasn't the best example, because you would have to have two samples or two events happening, right? So there will be some more examples, but this is a return of the comics. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. So he cannot say that the class caused it. He's just saying that it was correlated to the fact that he was taking the class. And this was the description that this had. Correlation doesn't imply causation, but it does waggle its eyebrows suggestively and gestures furtively while mouthing, "Look over there." Right. So, like, disentangling correlation and causation is quite difficult, and I think this is something that is then explored in more detail in probability and statistics classes. Cool. So in here I will also include, like, just to add to this point, from a book on probabilities, graphs, and causal models, where this is written. So by the way, I found this relatively readable. So I think a lot of the, as I was saying, the probability terminology for me at least was quite often really convoluted, and it was quite hard to get my head around it and to like extract what it actually is about, even though the concepts were sometimes simple. I think I found this to be relatively easy to read up until like the first few sub chapters in the first chapter were quite nice to read. Then they got into more like yeah, I can actually open it. Then they get into more details and more terminology, and then so it becomes less easy to read. But actually, this is quite nice intro to some of these concepts. I think, yeah, even this is actually quite good, because then you start, if you are interested at least in learning more, you can read up in here and learn a bit more about the terminology that is being used and the notation that they use as well. I think up until like all the way to here is still good, joint distribution, etc. Maybe like when you get to here, then it becomes a bit more complicated. So if you have some interest in this, maybe have a look at the first yeah, not even 17, like 8 pages or something of this short text, and it will kind of maybe show you the other formulas that I'm hiding from this class. Okay, but I will still like take a small excerpt from there, and that would be this observation that causal utterances are often used in situations that are plagued with uncertainty. This is some continuation of a sentence, but basically it relates to correlation and causality. We say, for example, reckless driving causes accidents, or you will fail the course because of your laziness. And I find it funny that this is a sentence that they are quoting from a research study somewhere. Well, knowing quite well that the antecedents merely tend to make the consequences more likely, not absolutely certain. So there is correlation, but not causality. Connected with this observation, we note that probability theory is currently the official mathematical language of most disciplines that use causal modeling, including economics, epidemiology, sociology, psychology, etc. I would add. In these disciplines, investigators are concerned not merely with the presence or absence of a causal connection, but also with the relative strengths of those connections, and with the ways of inferring those connections from noisy observations. So, you basically have a bunch of noisy data, and you somehow want to disentangle the variables that are the ones responsible for this, and also make some sort of guesses as to which variables are influencing which other variables. And so this was just chapter 1, and the book had many pages. You can like, if you are interested in this, there is a lot to study about this field in general, but I will kind of not bore you with the details in this class, I guess. Okay, the pause is imminent now, and after this we will look into some practical uses of probability. Before the pause we were doing a lot of theory about or concepts connected with probability, and now we will kind of look into the more practical cases or practical uses of probability, and basically that is statistics. So I think you will already know a lot of these functions and approaches to analyze the data, and probably just from using them from Python code. And some of these statistical formulas are, for example, the average, or a standard deviation, or a median, or something like minimum and maximum. And so the overall concept why we even have these is that we have quite like really hard to parse list of numbers, just bunch of data coming from somewhere, and what we want to do is somehow compress that data, maybe somehow extract the relevant information and show just that. And so in order that we can see kind of what is important in that data. And yeah, so basically that is the purpose of these. If we look into some formulas, I will introduce 2 of them today. and that is the average and standard deviation. And probably the average is really simple. So if you have a list on an input, and the list is just a bunch of numbers, for example, 201, then the average is basically summing all of them and then dividing them by their length. So applying this formula, which would mean something like this. So 2 plus 1 plus 0 divided by the n, however many we had. And that is sort of giving us the idea of the average sample, so like the most probable sample from that. And I guess if you don't look at like lists of length 3, we can have just like much more numbers, and in that case the average would be the most probable number from there, or sort of like getting the I guess getting an average from there. We can also use it in normal language. Okay, and so coming from there to compute the standard deviation, it has a different formula where we actually use the mean as part of that formula. So to calculate that, we look at sort of the distance of every sample, so every number from the mean, which means basically how much it is deviating from the average number. Again, this is like an example with very few numbers, and also it's example of a formula that we will not really be forced to write anywhere. In programming, a lot of these like functions are already defined for us. So we just call a function and it will give us the number. But the conceptual like understanding of standard deviation as looking at the difference between every sample and sort of the average statistic, and then somehow weighing that with all the data is something that could be quite useful. So what does this mean? Right. So what does standard deviation mean is that while average is sort of the average sample getting the number which is sort of most probable, standard deviation is giving us the information about the range in which the most of the data will be. So we can sort of see that the most probable will be around the mean value, but around it maybe mean minus 1 standard deviation, and then mean plus 1 standard deviation will be sort of the main bulk of the data of that list. Okay. So we will see this later in some visualizations where this will be more visible as well. So in practice, again, these statistics are somehow used as a means to compress the amount of information we have to read. Instead of looking at just a lot of points on a plot, we can look at like a more concise message, which would be just some average information from the data, and maybe having some sort of visualization where the standard deviation is. Okay, so we can so when we are working with images, we can also illustrate these concepts somehow visually, and we can start with photos, and that is the photos of faces. And so this is something like an average human face. So how they made these photos is well, it's not strictly just combining all of these images, because then it would probably not work as nicely around the face region. What they had to do is probably map whatever the facial markers are, and then kind of map all of those images together, so there is more pre-processing happening there. But still, this on this image you can sort of see the effect of averaging. So in the statistical data set of human faces, when you average out, it will sort of smooth out all the subtle differences that every one of us has, and kind of just strive for the most probable and most likely features in there. Of course, looking at this, you kind of have to always ask, sure, this is an average of some human faces. Well, especially if it's like a research which is somehow connected to social sciences, you always have to ask, this is human faces, fine, but where did they find the data set? Well, basically, when calculating statistics, the choice of dataset really influences what you will be getting. So this is the same thing as in the previous slide, but just kind of just biasing it by selecting samples from each one of the countries. And there were more examples here as well. But basically, how you sample your dataset, those statistics you will have. So maybe sometimes it's even actually hard to figure out how to collect the data in a way that it will not be messing up with the statistics, because statistics are nice because you can get like very concise information, just few numbers that are representing whatever you want to illustrate, but you have to kind of be careful when choosing the dataset so that you have good distribution of all possible samples in there. Okay, so slightly more about the concepts, and because we will be talking about some ways how to show these functions, how to plot some of those things that I was just explaining with the formulas. We should also talk about the concepts behind visualization, and one quite like important one is the overview plus detail. And so in that case, you can say that task of visualization is that you have some complicated data somewhere, and you want to somehow show the detail, so sort of like pick up all the what's important right now, all the small zoomed in cases, and also show the information about the context. So still offer all the information from the rest of the data. So I mean, visually, this is represented in some interactive design or interactive interfaces. Interface design? It has a name. User interface design, right? UI or user experience. But I think this would be UI probably more. And in that case, they have some research focusing on how to do exactly this. So how to sort of like allow the user to show just what they care about. So zoom in into the detail that they care about, but also to show the details of the whole dataset, which is, I mean, this is a slightly crazy one, but we all know something like this and we have been using it, and it's quite useful and quite handy, right? And when creating some visualizations in our code as well, we should kind of maybe keep this concept in mind, that when you show some detail of the data, you should also be able to show some sort of overview to show all the context. So what this means for the statistics that we were just talking about, for example, is I would consider an average of some plot of some numbers to be the detailed information, but to have some capability to say, okay, but then the standard deviation of those numbers is also going from here to here, is sort of a like it's something that gives us more about the context of that information. Okay. So in general, there are many types of plots that we can use to show the data. Sometimes just showing the raw data, meaning just plotting all the points on a plot, will be the best. But in most cases, it's actually better just to pre-process the data somehow, have a visualization which compresses the data, which somehow extracts the relevant information. Okay, and so not to stay in like the in just concepts, let's talk about a practical example of this, and that would be the box plot, which is a way how to visualize numbers. Kind of, let's imagine that we have a lot of measurements here, and the way how we visualize them is by this sort of this glyph, let's say. And this quite clearly tells us where most of the data is. So where the data around average and around median, and plus minus the standard deviations, where the data is mostly concentrated, but also shows us what would be sort of like the extended range of that, and also shows us what are the outliers from there. So this is a way how to kind of compress a lot of information into just one plot on a graph somewhere. So here is an example from some statistics I was actually doing with some research very long ago, where basically this is the almost raw plot where I was getting some numbers for analyzing some frames of a video, and in each frame there were a bunch of these processes that had to happen. I had to load something, I had to wait for something, I had to cut it, evaluate it, post-process it, and then save it. And so just to show these, you could always like look at these sort of plots. And what was happening there, that sometimes there were some kind of something was slowing it down, right? I was trying to figure out, okay, there is something happening here. I don't know what this is, but like there is something messing up with my statistics. Well, the way how to, well, this is almost impossible. The way how to look at this in a better way is sort of visualize it in the box plot, with box plots, where all of these were separated into each one of these categories and then shown into these sort of individual box plots. So in this visualization, I was able to see, oh, hey, actually, these two steps, let's say, or stages, were the ones which are the most responsible for the time it took. So these are the slowest ones. So, I mean, this gives me some guidance to tell me, okay, so if I want to speed this up, I have to probably focus most on this one, then probably on this one. But also, and this is something which is quite good, is that it shows you the outliers. So I was also able to just see, hey, and some of these saves, there are some problems maybe. So maybe these data points means that like when I'm saving something, maybe I messed up some programming part. So this is sort of the real world example where something like box plot visualization was useful. Okay, so you can also use this in comparing, right? So you would have different measurements in the world. Maybe one of those things would be a samples of like one species, and then this one would be samples from different species if you were doing some biology sciences, and then you could be actually comparing two different species, and in that case you could be comparing what are these regions of the quartiles, or where the data is most probably distributed, and also see all of the data around it. So I think we will not look into box plots today in the programming class, programming section, but I'm thinking of using or like saving some data, or maybe just making some data up and being able to generate something like this later, because I think this is something that can be useful in later, sort of when you're analyzing something, just as a tool that you can have in your, let's say, toolbox, as a script that you can run on any data and then visualize it. Okay, so this is a slightly adventurous plot by the XKCD. There is a visualization called the violin plots, which are these, and they are very suggestive, as this says, but they are also used in the real research. So this is not just a yeah, this is not just a joke. Okay, there are of course other visualizations. I will choose another one which is quite funny, and that is using Chernoff faces. So this is an example of lawyers' rating of 12 judges. So these are 12 data points, and for each of these judges, you would have a bunch of lawyers rating them, right? And every lawyer will kind of give different rating for the judge. So one judge will have bunch of data with them. So every of the each of the judges will have a bunch of ratings, and this is called something like high dimensional data, where every item in the dataset, and that item is the judge, has a lot of numbers associated with them, and those numbers are each one of those lawyers' ratings. So you could also say that each judge has a vector, which is somehow telling you some statistics they have. And so this is quite difficult to visualize. Most importantly, because people are quite used to showing things in 2D or maybe even in 3D, seeing things there. But when the dimensionality goes up, it becomes quite hard to distinguish even how to just plot it, because you cannot plot things in more than 3D on a screen. Even with, like, I guess you can include time, that's 4D, but what if you had more dimensions? And so the way how people kind of go at this is that they use glyphs. And a glyph is a sort of compressed representation, which is something like this, actually, where each of these parameters, each of these features that we can kind of maybe understand is something that corresponds to the rating. So maybe actually how much frowning these faces are, or how sad they are, I guess. I don't know what this meant exactly, but maybe the parameter which influences the position of the eyebrows was some, I don't know how angry they are. And then there is another parameter of how maybe satisfied were the people who were working with them, and that could be plotted into this thing. Well, I don't know exactly what they used in this case, but it's a way how to represent a lot of complex data. So this is a case where, it gives you really fast understanding, but then actually to unpack what's happening here is a bit difficult. Like, I don't know what's happening with this guy, for example, or and there is another kind of real world example of this with the ArcGIS, which is a professional visualization tool for maps, or even like a GIS software to show maps. And so there is a plot which is saying if people in the country prefer wine or beer, I think. And so they had these Chernobyl faces. Well, this is the raw data. And to show this, you had these 9 possible values. So either people prefer beer and buy it, or don't buy it, or wine, buy it or don't buy it. I don't know why they were doing the statistics, but it doesn't really matter. And they were mapping it into these images, and so these become the glyphs that then can be that then are used to, like, visualize something. So yeah, so this is one of the more funny examples of visualizations, and it's a way how to kind of map high dimensional data, or many dimensions of data, into points which are relatively easy to read if you have the correct explanation. Okay. So we are nearing the sort of the programming section, and that will include that will include some functions of sampling from random. This will include some examples of sampling from random functions. That's what I wanted to say. And so some examples which are more interesting for us than just looking at just random numbers in a row, or analyzing some statistics, could be getting these random functions to generate maybe images for us, to create something like 2D textures, or even to generate some terrains. And so this is really touching into some more complicated tasks, some which would be using some Perlin noise and stuff like this, which is not the same as just these random functions. These are some procedural functions which will create the noise, but you can also use these simple one as uniform or normal and Gaussian distribution to sort of influence whatever we are working with. Okay. So for those who would be interested, there are a bunch of links. I quite like this one because the first one, they generate, I think using Perlin noise, they generate a landscape, and then they simulate stuff like raindrops, and then so they come from like a pre-generated texture, which is a 2D image, and then they use some physical engine to sort of simulate everything else that's happening there, which would be this. I will use this case, this example, and show you this one. It's a video of a project that I was actually working on with generating landscapes. And this one is really far from the basic probability functions that we were using here, but it sort of at least shows you the direction where this can lead to. and so this one is generating landscapes from data, so not from some mathematical functions, but from data. Yeah, this is just to kind of show you a cool example of how all of this can be used. And so the idea is there that these textures are generated, and some parts should be forest, and some parts should be leaves, and some things should be roads. And then you have another model which is guessing the height, and then that one is giving you sort of like in combination, these two will give you a 3D model. So this was like a project, sort of. Okay, right. So yeah, this is supposed to be sort of like a proof that this can become more interesting as well. Because I understand that sometimes these theories become really dry, and like to explain or to get to projects like this is quite difficult. And honestly, even those functions that we were describing here, I don't think that you could go all the way to generate these landscapes with them, but it's a start, sort of. So you can, yeah, it's also the terminology that you can use in probability is then quite often referred to when using in my machine learning and stuff like this as well. Okay, so there is another research paper here from 2017, which someone else was doing some interactive terrain generation. And then on kind of just to bring these, the other topic for those who would be interested is text generation. There are data sets out there which have enough data of textures, and then there are some machine learning generated textures, which means having some small texture and maybe upscaling it and then having it be repeatable and stuff like this. Again, they are not using directly the same functions we were talking about, but sort of similar concepts can be drawn from there. Okay, so let's have a short pause in this case. So let's continue, and let's continue with the programming section. And today we will be exploring mainly the first part, using random functions in Python. So we talked a little bit about some of the sort of like the theory behind naming some of those functions, the uniform random distribution and the Gaussian normal random distribution. But let's now try how to actually use them. And then let's use them to generate some textures, even though these will be basic ones. So the statistical analysis of data, I think we will get into that more in the next classes. I think if people would be interested, I can go into some more sort of visualizations of some data, so sort of compressing some measurements from somewhere into nice plots, something like this, because it's something that you probably will encounter again and again when programming with Python. And some visualization of some measurements is part of any sort of work, because sometimes when we are programming we can somehow store some of the values, and still just to show what's happening is sometimes quite good. So yeah, more about that later. So if all of you could start with today's lecture's starter code, which is something which is located on our GitHub in the 7th week, so statistics and probability, and here the random function starter. It is relatively short, so it's this one. I will copy paste the link into here, and so please open it in your Google Colapse. Should I show again how to open stuff in Google Colab, or everyone is more or less? I think we did that enough times that everyone should know how to do it. Tell me if someone needs some help with it, maybe. Okay, yep. So let me describe the code a little bit and explore what we have there, and then there will be some task for you to code as well. Okay, so let's see. So this is more or less the code that you will open up. What we have is some examples of how to actually use some of these functions that we have been talking about. So I will go through it basically line by line. First, we will be using the NumPy, which is a library which is quite often used when working with statistics or with with lots of data. So from there we will use two functions, normal and uniform, and these functions work as like a generator to get a random number which would be corresponding to normal distribution or uniform distribution. So maybe I can separate this code a little bit, and just to show what's happening, let's say that we are sampling here from the function called normal. Well, what this does is that this will sample or get us one number, one sample from that, from normal distribution. So if I try it and then print it, oh yeah, it has to connect and everything. But when that happens, I should get a one sample generated from normal distribution. Oh, okay, to get rid of that. Okay, so yeah, this number, and I can keep generating new one and new ones, is a number which is generated from the normal distribution. The two parameters that we will be using are, first one is the mean, so the number that everything sort of revolves around, and then the second one is the standard deviation, which influences how far the data can get. So we are starting with this function with setting 0 and 1. So more or less, this should be corresponding to this red plot, right? So we are getting numbers from -3 very rarely to +3 as well, very rarely, anything around that. So if we just try it, it more or less works. If I try the standard deviation to be something very small, this should make the sampling be really near around the number 0. Okay, so when we change these two parameters, we are sort of changing the model. So let's see on the slides. If we would like to mimic the random generator function as this green one, we would have to copy the -2 and 0.5 as the parameters. So mean -2 and 0.5 as the standard deviation. And then if we try it again and again, we are supposed to be getting numbers around -2, and then more or less in that region, right? And this is quite nice. It's working. The theory is correct. So we should be getting numbers around -2, and then yeah, sometimes get something as low as -4, but quite often get in this range. Cool. So that's the normal distribution, and this would be the uniform distribution. So using this function, I can get numbers which are uniformly distributed in between these two boundaries. So this should correspond to sort of these two plots. However, I sort of define it as with the parameters. So let's see the results from 0 to 1. All of these numbers, well, they should be different, right? They should be uniformly sampled. All of them should sort of fall into between 0 and 1. Nice, it seems to be working. Well, what's hidden here and what I cannot really see when I'm just looking at this is that all of these numbers should be sampled uniformly. So there is equal probability that all of those numbers will fall. Well, that's quite hard to show on this example because we are just getting one and then printing it immediately. And so the way how to do this is we can change this code by adding size equals to something, and this means that instead of generating just one number, we will generate a whole list of these numbers with the size of 5. So let's see it here. We are generating this amount of numbers. So size 5 is still quite small sample. We are getting some numbers here, but it's still relatively small. Okay. We will get to plotting, but maybe now I will add some part of the code which you will not have in the starter code, so maybe you can rewrite it. If we generate some amount of samples here, so let's just copy this one to here, and let's change the size to like, yeah, 5,000. Why not? Sample normal, call it large. So let's call this, let's get this 5,000 numbers which are from that distribution. If I then write what is the size of that sample, well, it's 5,000, right? Because we asked for 5,000, so this works clearly. I can use some statistics. So NumPy also allows us to get some statistics of the data. So for example, I can say, yeah, I would have to import NumPy. Import NumPy, and then I could say NumPy dot mean, right? And get the mean number of these, means the average number that I would be getting, which is basically this. And then I can call it something like mean is this. And by the way, I will share the solution code later as well, so this will be there as well. But not immediately after the class, because I will have some tasks to try for you. So we generated some numbers, and we know that we created numbers with mean around 0. But we sampled 5,000 of them, and then later analyzing the samples that we created, we get that the mean of the generated numbers is 0.01, which is close enough to the mean, which means it's kind of working. But if we look into the really early slides, somewhere in here, basically we went from here, from this case of having kind of knowing what model we have, back into this case. And so what happens is that we generate some samples, but some of them will sort of have some randomness in them. So there will be some amount of data that's not here, but it's more here. So later than calculating the statistics on the generated samples, sort of trying to go from models to samples, and then from samples again to a model, you will see that there is some difference because it just sort of changed over the time. Right. Because we have generated 5,000 samples. I mean, if we generate 10 samples, it will be even more different, right? This is not reliable enough sample size to give us what we sort of want. Whereas if we generate something really large, then it becomes more and more close to what we actually wanted, so what we asked it to do. Okay, the same, we can calculate the standard deviation, right? And so this is again this is sort of recreating what the two parameters were. So this analysis doesn't have an access to these two numbers. It has to sort of recreate it from the data that we generated. Okay, so yeah, this is just like a by the way analysis point with NumPy. Yeah. Okay, so this would be this, and I guess it's relatively interesting to still show these examples and like write these samples, but maybe there is a better way how to show it, and that is by plotting. So that's what's happening here. Which is the same way as before, we generate 5,000 samples from the normal distribution, and then we plot these into a histogram. So what is a histogram? Histogram is this sort of plot which assigns all the samples into some amount of bins. So I told it, hey, you have 50 bins that you can distribute between this data, and then these bins will you will have to choose for every sample into which bin you throw it in. And so this is a visualization, so something that we saw in the slides here, right? This is the visualization of how many samples were at that sort of value. So let's see this. I mean, we have just seen it, but like we can generate it again and again, and we can see that 5,000 samples is quite good because it makes a very sort of predictable shape here. Also, this is a way better way how to show what this normal function looks like, because we are creating enough samples and then plotting them. I can then change this into something like 100 and then see that the samples that I'm generating right now are around 100. And let's see that I would want to generate around 100 with standard deviation 1. So yeah, most of the numbers will fall here. Let's say that this could be 50, and then in that case I will see that most of the numbers will actually fall from 30 minus 50 and then plus 50, and then still there will be some drop off here. And so this is like a way how to show how these visualizations really work. So if I go back around 0, yeah, okay, and maybe show something with a very small standard deviation, so everything should be really around 1, I will see that quite a lot of the samples will actually fall in between 1. Even smaller, this should all sort of figure out this as yeah, this is all very close to 1. I mean 0 in this case. If I return it back to 1, it's the normal one, and if I set it to something large, this hill will sort of spread out more, and it will cover larger areas like this. So this is a way how to effectively show what we had here. The different like the different plots here. We can just sample from those models and get the samples and then show them on a plot. Okay, so the same as we did in here for the normal function, we can do it for the uniform as well. And so this is working nicely for 500 samples. We say it for numbers between 0 and 1 and make it. And then we generated 5,000 numbers which are in between 0 and 1. This is, let's say that this would be 100. If the population is smaller, or this size is smaller, then it still is with the same probability between 0 and 1, all of them, but the trend is not really visible because some of them will fall there. And this plot is nice because when you just print it like this, you have no way of telling, like, of getting the information from this data. You can see it's all sort of like around 0 point something, so it's probably between 0 and 1, but you have no idea how it's distributed. So something like this is quite useful. So let's see. Let's the larger the number, the larger amount of samples. So the closer to the to a sort of like a square brick we will end up. We can also change this, so we can go from -1 to 3 or something, and then it will distribute amongst -1 all the way to 3. Right. So basically, this is a way how to sample random points from some range in a way that is predictable for us, which is good. So, for example, we could use it to generate from samples from 0 to 500 and know that it will fall here, and then sort of look at those numbers and maybe even convert them into integers, and then we would be getting some values that are usable as to maybe address them as pixels. So to carry on that thought, I will go into the task section of the programming of this Python notebook, and that is to use these random functions to create some images. Right. So in here we create an empty image of 500 by 500 pixels, and here is nothing because it's all commented, and here we just display it. So we are plotting it as integers, so a number 0 is dark pixel, a number of 255 would be a black pixel. I mean white pixel. So let's have one white pixel on the coordinates of 33 by 33. This would mean all the 3 channels, so all of the RGB, or we can say, yeah, all of those. Let's plot it. Oops. Well, yeah, I did not import NumPy. Okay. Well, I imported it, but I didn't call it as NP. Quite often in the code you will see this, which means that everyone is lazy to write NumPy over and over again, and they just write NP. So when you see in code NP, this is NumPy. Okay, so this is the black image, and here this very hard to see thing is the white pixel. Well, yeah, looking at pixels is terrible, so let's see if we can do something better than that. We can enlarge this into a whole block. So this is a way how we can address in NumPy lists whole areas. So this means from 60th to 80th, and then from 60th to 80th again. And then all of those 3 channels, set them to 255. And in this case, yeah, you can color the whole thing. You can also say that this is the red channel, this is the green channel, this is the blue channel. And so we can say that, yeah, maybe just color the red channel. And so in this case, it should end up being red, yeah. And so, yeah, you can, I mean, this is very low level accessing just image to change the values of pixels. Okay, so why am I even talking about all of this? I mean, I'll hide it again. But all of this is a sort of preface to what you will be doing in the task. And that is, I want you to generate here the sort of image that we could have seen in our slides around here. So something like this. And so how to do this is that, let's say, we are generating a bunch of numbers. Let's say that those numbers are, let's say that we want to, we are generating at random locations and then coloring them pixel by pixel into white. So if I allow this again, and if I allow this again, this means that the 30th and 30th pixel here will be white. If I change this into using one of those random sampling functions, so let's say that the first one, let's say, if I say random pixel 1 and then have this, so this will generate us one random number, and then random pixel 2, and this will generate us another random number. And then instead of 33, 33, if I kind of place them here, then whenever I am creating a new one, oh, what's wrong? Right, okay, so because I'm getting a number which is, yeah, it's always good to print them. I'm generating a number which is float, I think. So if I just print it here, yeah, I generated something like this. So I need to convert them into integer. There was a question, I heard it, I will look at it. Oops. Okay, so now we generated a random location and random location and colored it to white. Now I don't know where this was because I cannot see that one, but one of these pixels is actually white. Yeah, it's here actually. So this pixel is colored to the white. Let's see the question. It's a float. Yay, okay. Yeah. Yeah. Right, so, well, this is a way how to find kind of one pixel in there and to color it into white. The task here is to just fill the image with a lot of these, not just one, but basically this means sort of repeating this function again and again, probably in a loop, to fill this area with random white pixels. Or sort of, if you want, you can then start spraying over different colors. That doesn't really matter. That's up to you. But what I would like to for you to try is to test the normal and the uniform distribution, and so that you can generate images which sort of correspond to these and see the difference between these two. Okay, and so the task also will be to set up this these two functions correctly and sort of explore what it does when different parameters are used there. So is everyone clear with the task? It should be relatively easy. It's not like too difficult, but it should maybe illustrate how to actually use some of these random sampling functions in the code. So in theory, when you write it here on this basic example, you can then later use it on your own stuff as well. And so sometimes you really actually need all the numbers that you're getting are uniformly sampled between some two numbers, or some different numbers that are really just concentrated around like one particular number. And so to be able and to sort of to know which one of these random sampling functions to use is actually something that can be later useful as well. Okay, so this is more or less it. I will I will leave you guys with this task, and this will be the end of the class. The task will be to sort of generate the image here and have something nice happening or interesting happening, sort of explore the two functions. And the homework for you guys will be to fill in a quiz that I will show here. And as part of that quiz, there will be some 3 basic questions about the topics that we discussed today, some really simple questions. And then I will also probably open up a possibility for you to upload some of these examples that you create right now.